All right, thank you for tuning in, guys. I'm here to give you a little bit of a walkthrough on some of these soil taxonomy classifications as you work on your soil taxonomy challenge. So I'm going to start by going over soil number 2, which is the first soil profile that I originally demonstrated in lab, but that did not go quite as planned. I missed a couple important details, so I want to take the time here to give you a good summary of what to do there. So I will share my screen and take a look at what we're working with. So, okay, here's the BB Learn page. Important things to have will be in lecture notes. Lecture 17 for soil and moisture temperature regimes. And then also go over to homework where we have our soil taxonomy challenge folder. So I also have, so I've got the lecture 17 moisture and temperature regimes. I've got my soil info packet here open already. And then a copy of the answer key that I'm going to be filling out along with you guys, and then a copy of the keys booklet here online, so you can see where I'm reading. So let's start by taking a look at our soil information here, and I'm going to go to the very bottom where we have the actual picture of it. So you can't really trust these horizons. I think they line up for this profile, but not for some of the other ones that I have you look at. So these are very old descriptions, so you can't really trust them. Rely on the horizonation in the official description. But we have a thin A horizon up here, a BW section up here, and then we go to a fragipan with some clay accumulation. So you can really see the strong prismatic structure just kind of popping out in the picture. So this is a good example of, it's a grade 3. It's really strong, easy to see. Really exciting prismatic structure in this fragipan here. And then we do have a thin E horizon right there. Hopefully you can see my mouse on those screen share. But we've got that E horizon above the fragipan, and this BW weak development, and then a thin A horizon. So it's really dark. We've got that dark topsoil color up there at the very top, but it's not that thick. So that kind of gives us a good idea of what kind of soil we're working with. Let's go back up to the top and read our parent material. We have volcanic ash influenced loess in the upper part over loess. So it's loess parent material. Technically it's made of volcanic ash, but we had our volcanic ash erupted from probably Mount Mazama, and then it settled on the landscape and set in place. But then winds picked up and carried this ash elsewhere. So, you remember the definition of loess parent material is just like silt and fine sand size particles transported by wind. So even though this is it's volcanic ash influenced loess, it still counts as loess parent material. It's not exactly volcanic ash deposited directly by a volcanic eruption. Something to think about there. And what else? I think that's good. I think I have a pretty good understanding of what we're working with here. Now, just to read through the horizonation, we've got a thin A horizon, BW is that E horizon, and then a BE transition into BTXBs for most of the bottom part of the profile. Okay, so I'm just orienting myself here with what the soil profile is. Now let's take a look at what we're filling out here. So let's start with this top box, the temperature and moisture regimes. We have some hints here that are going to be helpful. Our seasonal temperature difference is greater than 6 degrees Celsius, and it's not too wet or dry. So we're going to go over to lecture 17, which Jody has posted for us, and we talked about this in lecture. Let's zoom in on this temperature table here. So mean annual temperature at 50 centimeters deep in the soil is not necessarily what we have. So I'm going to flip back to the our soil info packet, which is the next tab right there. And it's given to us right here. Mean annual air temperature in degrees Celsius is 7.3. So our mean annual soil temperature is, I guess we could round it down a little bit, but in this case, it's not really going to matter because our 7.3 degrees Celsius soil temperature is less than 8 degrees as indicated by this table. Our seasonal difference is greater than 6 degrees Celsius. So we're right here in this frigid box. Frigid is our temperature regime. So I'm just going to put an X right there and then move on. So, we have cryotic, frigid, mesic, and thermic. And then we also have these iso and hyper prefixes. How do you know if you need one of those? It's not that complicated. You just keep reading in this table. If you have a really hot soil, it's hyperthermic. That would be in Florida and South Texas. I think that was a test question that you guys just had. So this is what Jody was asking about then on a test question like that. Or if the seasonal difference is less than 6 degrees, it's pretty constant all throughout the year temperature, then you'd probably add the ISO prefix there. So we don't have either one. We'd leave those ISO and hyper blank. It's just frigid now for us. So let's scroll up a little bit to moisture regime. And here, a similar table for soil moisture regimes. So our hint is not too wet or dry. Precipitation is unevenly distributed. I'm just giving it to you here, essentially. So our concept, not too wet or dry with uneven distribution. This is going to be the xeric, our Mediterranean climate, which is what we have here on the Palouse, where it's warm. They're warm and dry summers, and then really cooler, more wet winters, an uneven distribution. So it's not too wet or dry on the whole over the year, but the summers are going to be very dry. The winters are going to be very wet. If it's not so unevenly distributed, it's an ustic moisture regime where it's not too wet, not too dry, but precipitation falls evenly across the year, or you have more in the summer. Xeric environments will have more in the winter and less in the summer. Okay, frigid and xeric off to a good start. Now let's take a look at the epipedon. Let's go back to our info packet here. We have our A horizon from 0 to 3, and then we go to BW. So let's take a look at our epipedon definition. This is going to be in chapter 3. So I use these bookmarks to get around quickly in the virtual edition of the taxonomy book. And here we go, right off the top, it's diagnostic surface horizons, the epipedon. So the epipedon, Greek for epi, over upon, or the pedon, soil. It's a horizon that forms at or near the surface in which most of the rock structure has been destroyed. So it's really, it just means we're at the top part of the soil. It doesn't mean the very first and only the first horizon. It can be multiple horizons in the epipedon. It just means in general, we're looking at the topsoil as opposed to the subsoil. So it's up to us to determine how far down this topsoil includes. We can kind of go one by one. There's not that many to choose from. If you have lots of human altered or human transported material in the epipedon at the surface of your soil, it could be anthropic, like urban soils. Tholistic and histic are both really organic rich. We start off with an A horizon. It's not an O horizon, really deep. Histosol is what I would be thinking about there. So I'm going to skip both of those actually. Melanic requires andic soil properties and essentially molic. So it's a mollisol for andesol, a molic epipedon for andesols or andic soils. We'll keep that one in mind, but I want to start off right here with molic epipedon. This is going to be a pretty common one, and it's going to be the one you want to probably think to test first in most cases. So this first requirement for molic, when dry, either both structural units with a diameter of 30 centimeters or less. This just means the particles in the soil are less than a foot in diameter. So that it's like serious rock chunks that we're dealing with. We want to rule that out. So if you have greater than 30 centimeter diameter particles, you're probably not soil at that point. You're still really thick rock chunks. Okay, so we're good there. We're dealing with soil. We're dealing with a silt loam at the top of the soil, actually. So we have rock structure, including fine stratifications, less than 1/2 of the volume in all parts, and one of the following, A, B, C. For item A, we have both of the following: a dominant color with a value of 3 or less. So this is our dark color for mollisols. Value is 3 moist or 5 dry, and the chroma is 3 or less moist, or certain other characteristics there. Okay, so let's just check our colors for now. Let's flip back to the soil info packet. Our A horizon, we meet the color requirements. It's a value of 3 and a chroma of 2 when dry, and then it's 2 when moist. So we definitely hit the color there. However, it only goes down 3 centimeters, which is probably not going to be enough to fit a molic definition. Getting down to 23 and then 43 centimeters, we're much lighter. We're 7.5 YR, 5 for the value, 3 for the chroma. That doesn't fit the molic definition anymore. So let's just flip back and keep keying this out. So far we're good with color, at least for the first 3 centimeters. We can check our base saturation by ammonium acetate of 50% or more throughout. So let's go to our lab data here. This is in the same soil info packet. This is the second page now. Let's try the third page. Okay, third page of lab data. And we're still focusing near the top of the profile. So we got this A, BW1, BW2. Our base saturation by ammonium acetate is 76, 57, 96%. That's going to average out to be around, around 75%. That is greater than 50, I think was the key here. Yep, 50% or more base saturation. We definitely meet that. Organic carbon content of 2.5% or more, 0.6, 0.6% or more for various qualities. That's quite a bit. We can check. Do we have organic carbon content on here anywhere? Let's scan through this lab data. Here's total carbon, 6% at the very top, and then we have 0.8% for 3 to 23%. So maybe we have enough organic carbon, but I'm really concerned about the color, really. The minimum thickness of the epipedon, it has to be at least 25 centimeters in most cases, but less, only 10 centimeters if you're right above a densic, lithic, or paralithic contact. So if the profile is limited by like an R horizon or a CR or a Durapan or something, it's a really shallow soil profile. You don't necessarily need to have a super deep, like absolute depth of the molic epipedon in order of topsoil to have a molic epipedon. They kind of allow for that if you have a really shallow soil. We have a pretty deep profile. There's nothing really limiting near the surface for us. So our requirement is going to be, I believe it says 25 centimeters, and our color does not match that all the way down. So we're going to rule out molic epipedon. Other things it could include pelagian and umbric here. Umbric is kind of similar. It's going to key out pretty similar to molic, except for this line right here, base saturation by ammonium acetate of less than 50%. So this is accounting for low activity clays, really the ultisols. So like our melanic epipedon is like a molic epipedon for andisols. I would say umbric is like a molic epipedon for ultisols. That's not what we have here. That just leaves the ochric. So ochric epipedons fail to meet the definition for any of the other 7 epipedons because it's too thin or dry. The color doesn't match. The organic carbon doesn't match. It's a catch-all. So soils have to have one epipedon. They cannot have more than one. They can have one and only one. So I'm going to put an X right there for ochric right away, where we don't match the color we don't match the color deep enough for molic epipedon. Okay, now we're going to flip to subsurface horizons. Going back to our soil info packet right here, and I'm going to look at the subordinate distinctions. So our epipedon is like our topsoil. Subsurface horizons, we're going to be looking at the subsoil pretty much now. Going through the letters, we have BWs. BWs usually makes me think cambic, so I'll keep that one in mind. An E horizon is making me think of albic materials or albic horizon. BT is argillic, maybe, and then BX is a fragipan, is usually what that means. So there's quite a few options for us right away. So let's go back and start trying to fit some of these to their definitions. Back to the taxonomy book, and we'll keep scrolling down to our diagnostic subsurface horizons. Okay, this is what we're going for. Right here, we've got albic. Albic horizon is an eluvial horizon, right? Our E horizon, at least 1 centimeter thick, that has 85% or more by volume albic materials. So if you don't know what albic materials are, this is kind of handy because we have the virtual version. We can just search for albic materials and then pull up the definition of it at some point. Let's see, albic, here we go. Albic materials, all right. The required characteristics to have an albic horizon or albic materials in the soil are really based on color. So if the chroma is 2 or less, while the value is 3 moist or 6 dry, or 4 moist or 5 dry, if it's albic, or it can be, it's really just based on the color. So what is the color of our E horizon? That's the one I'm considering for albic. We have 98%, so greater than 85%, and 7.5 YR, 8.2. That's a really high value, a really low chroma. So this means we're on the very, like the bottom, or no, we're on the top left of the color page. It's really pale white. Okay, that we saw that in the picture. That's kind of what we expect for E horizons. So we fit the color requirements of the albic materials. Now let's go back up to, let's see, where we came from, right there, albic horizon. So we're at least 1 centimeter thick for sure. And this is all extra information about where it can occur, but doesn't necessarily have to occur. So for my purposes, we fit albic. I'm gonna put an X right there to check our subsurface horizon as albic. Okay, you can have more than one subsurface horizon though. There can be a lot of things going on in a soil profile at once, especially in the subsoil. And argillic is the next one we want to consider. So it's normally a subsurface horizon with a significantly higher percentage of phyllosilicate clay than the overlying soil material. So in our profile, we go from silt loams to where that BTX starts, silty clay loam. So we definitely have an increase in clay and probably evidence of clay accumulation. So we must meet both of the following requirements, A and B. We have to have at least one of the following here. Argillic horizon has to meet particle size class criteria for pretty much anything but really sandy. So that's what this is saying. It must be at least 7.5 centimeters thick, or if it's a really sandy or sandy skeletal, it has to be at least 15 centimeters thick. So we're silty, we fit in this one. We have 7.5 centimeters as our depth requirement. And evidence of clay alluviation in at least one of the following forms: clay films lining pores, clay films, clay bridging, something like that. So that's what the T horizon usually means. To be absolutely certain, we can check in the profile descriptions here. We've got clay films on all faces of PEDs, clay films on all faces of PEDs. That sounds good to me. So I'm just gonna mark argillic, flip back to the taxonomy. Is there anything else we need to consider here? If an eluvial horizon remains, so we've got that E horizon, and there's no lithologic discontinuity or change in parent material between it and the illuvial horizon, no plow layer, right? Then it must contain more total clay than the eluvial horizon within a vertical distance of 30 centimeters or less. So let's look at our depths now in the lab data. Our E horizon goes to 71 and our clay percentage is 19. And then within 30 centimeters, looks like we're up to one of these two horizons here. Our clay percentages are 22.5, 22.2 and 24.4. Let's just kind of take this all the way through. It's less than 50% total clay. That's not us. The eluvial horizon, so the E horizon, we have 19% clay. It's between 15 and 40. The argillic horizon must have at least 1.2 times more clay than the eluvial horizon. So our argillic horizon is pretty much these bottom three where we have the T subordinate distinction. So do we have at least 1.2 times the 19% clay? So we'll take 19, grab our calculator, multiply by 1.2. Do we have at least 22.8% clay in the argillic horizon? Yes, we do. We're at about 22.5. We're at 24. That average is around 23. So we do meet that requirement. So it's definitely argillic. Proven. Okay, cambic is the next one on the list. We got that BW horizon. So I'm thinking cambic is an option. Let's read this one out. The definition of cambic is very encompassing. It's very generous. It includes lots of soils. However, when we get to this item right here, number 3, cambic horizons have to have properties that do not meet the requirements for anthropochiastic, these epipedons, a durapan or fragipan, argillic, calcic, and then this whole list of subsurface horizons. So we do meet the requirement for argillic horizons there. We just marked it down. So that means we do not fit cambic anymore. Cambic horizons are designed to include lots of things, but as soon as you, as a soil profile, have something else to consider as a subsurface horizon, you no longer qualify for cambic. It's something that's there if you don't have anything else, but you still have soil development like a BW horizon. As soon as you add that BT or BTX or something, you have other subsurface horizons and cambic no longer fits. So actually, let's not put an X there. We just have albic and argillic so far. Cross that one out maybe. Okay, durapan, we don't have any M's. Fragipan is the next one to consider because of the X subordinate distinction. Let's read about it for a little bit. Right here. same page. Fragipan required characteristics. To be identified as a fragipan, a layer must have all the following characteristics: 15 centimeters or more thick. We are the whole bottom half of the profile pretty much, so we fit that. Evidence of pentagenesis, which is our development of structure. We have that. The layer has very coarse prismatic, columnar, or blocky structure of any grade or weak structure of any size. We've got very strong prismatic structure. We saw that in the picture. We can read it off of the list right here. Our horizonation, starting at the top of it, we have very coarse prismatic structure, coarse prismatic parting to strong coarse angular blocky structure. We have compound structure, which that means, and then we still keep prismatic right there. Okay, so that's good. Let's go back to the taxonomy. We're good. Air dry fragments of natural soil fabric, 5 to 10 centimeters in diameter. More than 50% of the layer slakes when they are submerged in water. I don't think that shows up on our lab data. This is how you can tell a fragipan from a durapan, I believe. Also, this layer is not effervescent. That's telling a fragipan from a petrocalcic layer, a BKM horizon. Okay, lastly, item 5, the layer has 60% or more of the volume. Firm or firmer rupture resistance class of brittle manner of failure at or near field capacity and virtually no roots. So it's root restrictive, and it's really hard to break. It's brittle. I see that right there, brittle, and then firm or extremely firm. You think that's in here somewhere? Extremely hard, extremely firm. Yeah, absolutely. This is textbook fragipan. So let's mark that in with an X. Gypsic, candic, natric, petrocalcic, spodic. None of those are honestly going to fit because of our subordinate distinctions. We just lack those. Hopefully you get to see some of those in future pages of the packet. Okay, let's keep moving right along to the soil order. I'm going to use the official taxonomy book here to do that. And I think I skipped to chapter 4 for that. Identification of the taxonomic class of a soil, which is our key to soil orders. Okay, so remember that soil orders get more broad. The definitions for each order gets more broad as you work your way through the key. So you have to start at the top and work your way down to make sure you don't make any mistakes. So the definitions start narrow and they get more and more wide. So if you have literally any type of soil at all with permafrost in the top meter, it's a gelisol. You don't have to ask any other questions. Gelisol is the most restricted definition. After that, we have histosols. With really deep O horizons. We don't have either permafrost or the O horizon, so I'm skipping past both of those. Next option is spodosol right there. So starting back here at letter C, we do not have a plagan epipedon or an argillic or candic horizon above a spodic horizon, and one or more of the following. We don't have that spodic horizon, that combination of E and a BHS or a BS, that evidence of podzolization. We don't have that. So I was just ready to rule it out right away. You can work your way through, yeah, AP horizon containing 85% more spodic materials or spodic horizon with all these characteristics. We don't have that spodic horizon. So even though it might be probably an option for some North Idaho forests. So we are going to skip past spodosols because we're missing that horizon. Now this is an option, andisols. Remember, we have that volcanic ash influenced parent material. So we have to have andic soil properties in 60% or more of the thickness of the mineral soil surface, really is what this is saying, with kind of depth dependent. So let's find our andic soil properties definition. I believe that's on page 18. So let's scroll up here and down a little bit. Candic, 15, 17, 18. Okay, so starting here, andic soil properties. This is an interesting figure that Jody showed you guys in lecture. So if the volcanic glass content here on the y-axis is high enough, along with the combination of aluminum plus half of the iron percentage, adds up to one of these numbers here, you can fall on andic soil properties. So less than 25% organic carbon, which is true for us. Let's look at our lab data, have that ready to go, because this is what this is all going to be about, right? Here's our carbon percentages. It's less than 20 for sure. We don't have any deep O horizons. And then now our ammonium oxalate extraction data is right here. Maybe I'll zoom in a little bit more if you guys can see this. Okay, ammonium oxalate data right here for the first 3 horizons is all we have. So our aluminum plus half of the iron is calculated already for us. Pretty nice. We have 0.44, 0.37, and 0.21. So it's that these are pretty low numbers, but let's read what exactly we need. A bulk density measured at 33 kilopascals, water retention of 0.9 grams per centimeter or less, low bulk density. This is a little disappointing because it would show up right here in bulk density. We just don't have that data, unfortunately. I think we can still do our keys without it. Still key this one out. So we're not really sure about that. Our aluminum plus half iron content equal to 2% or more. It's not 2% or more. You don't have to add all these up, right? That doesn't really make sense to do because they're percents. It's not a total of anything. We're less than half, honestly. So that's really a bummer. We don't even make it to the 0.5 right here on the, looking at the x-axis, aluminum plus half iron percentage. We're right here. We're really low on the list. And our volcanic glass content, we can read off of one of the last pages of lab data right here. Let's zoom in a little bit more. Look at the mineral interpretation key. GC is glass coated grain, GS is the glass. This is percent right there based on optical grain count. Our GS for glass is 13 in the first 3 centimeters. Then in the BW horizons, it's 4% and it's 3%. So really low volcanic glass content as well. We're like down here in this very bottom quadrant. So we don't fall into this Andic soil properties window of the graph. So we can't key it out as an andesol then. This is a mistake I made during lecture or during the lab portion. I saw that volcanic ash. I wanted to say it was a andesol, but it's not. So back to the keys, or no, we're still on the keys. Back to the soil orders, chapter 4, and we can rule out andesols. I'm going to rule out oxasols right away. We don't have oxic horizons or the right climate conditions. We don't have a vertisol because our clay percentage is so low. There's no slick sides. There's no shrink swell concern here. Then iridosols, we don't have that arid moisture regime, right? We're xeric. We can skip past that. Ultisols. Okay, yep. After iridosols, we have other soils that have either argillic or candic, but no fragipan. So we do have argillic, but we do have a fragipan, so we're ruling that one out. So it's either 1 or 2. So we don't fit 1, but we might fit 2. A fragipan and both of the following. So we have the fragipan, that's good. Either argillic or candic horizon. Yes, and item B, base saturation by sum of cations less than 35% at the shallowest of the following depths. So let's take a look at our base saturation by sum of cations. So back to the lab data and back to the first or second page. Third page, okay, here's base saturation on the top on the right side by sum of cations. So before we were looking at by ammonium acetate extraction, now this is sum of cations. We're greater than 35 by a lot, by quite a bit. So we're in the 50s, 60s, 70s, just increasing as it goes down. So we do not fit ultisol. Skip past that one. Then mollisols, we need a molic epipedon. Don't have that. We keep going to alphasols. So item J here. Alphasols are all other soils that do not have a plagan epipedon and that have either an argillic, candic, or natric horizon. That's us. Or a fragipan that has clay films. So we fit both of those things. We only needed 1. So this is saying alphasols are literally any soil that has an argillic horizon. Does having a BT in the soil profile make it an alphasol? In this case, we fit the definition, but no, just because you have a BT horizon in like a spodosol or an andesol or ultisol or something, it means you fit the definition for alphasol as well, but those ones key out first. Their definitions are more restrictive than alphasol right here. So if we were to keep going, the definition gets more broad and more broad until it's literally everything else. It just says other soils. So that is an entisol. But we stop right here because we have an alphasol. So we're going to type that in right here in order as alphasol. And then onto the suborders. So alphasols are on page 43. That's also chapter 5. They go alphabetically from there. So skip right to the alphasol chapter. And we're going to pick out our suborder. So before I dive right in reading line by line, I like to take a peek at what the suborders are. Aqualfs, cryalfs, oostalfs, xeralfs, and oodalfs. Okay, so they're all based on the moisture, like the climate conditions. We know we're xeric, so I'm looking right at xeralfs. Any alphasol that has a xeric moisture regime. That's going to be us. So let's go Xeralfs right here. And then onto the great group. So we have to go to page 79. Let's skip right there. And find our Xeralfs, key to the great groups. All right, line by line, we'll go Xeralfs that have a Durapan within 100 centimeters of the soil surface. We do not have that M horizon, so we're skipping Xeralfs. Xeralfs that have a natric horizon, that's not us, that's the N subordinate distinction, don't have one of those. Other Xeralfs, so non-Duri Xeralfs or nature Xeralfs that have a Fragipan within 100 centimeters of the mineral soil surface, that is us. We're a Fragixeralf right there, nice and easy. Fragixeralfs. Okay, and then page 80 for the subgroup. Fragixeralfs right here, key to the subgroups. Okay. Fragixeralfs that have throughout one or more horizons with a total thickness of 18 centimeters or more within the top 75 centimeters, a fine earth fraction. So our particle size class is essentially sand, silt, and clay. With a bulk density of 1.0 or less, which sadly we don't know, and aluminum plus half iron percentages totaling more than 1.0. So we looked at that before, right? They were 0.44, 0.37. They were really low. We don't really add them. We don't add those together. The totaling here means aluminum plus half of the iron percentages. We don't have more than one. If we did, there would be more like stronger andic properties of the soil. It might be more fresh or just better preserved or something. It would be an andic Fragixeralf. So we have to rule that out because of our Al plus Fe, half Fe percentage. All right, next one is Vitrandic Fragixeralfs. We have to have one or both of the following: more than 35% or more particles within 2 millimeters or larger. So if it's really rocky, if we have coarse textured soil with coarse fragments, and more than 2/3 of them are cinders, pumice, or pumice-like fragments. So let's look at our texture data here. That'd be on about the first page of lab data. So our sand, silt, and clay here, and then I'm gonna follow this all the way over to the right where we have rock fragments, something greater than 2 millimeters. Yep, rock fragment units in millimeters, anything greater than 2. I see this column right here. It's really low. It's 3% or it's 5%, which is really low. It's not going to be 35% or more. That's not us. Could this be us? A fine refraction contain 30% or more. Yeah, 30%. So at least 30% or more particles that are sand, silt, or clay, silt or clay, I guess this is 0.02 to 2 millimeters in diameter. And 5% or more volcanic glass, and Al plus half Fe times 60 plus volcanic glass has to be 30% or more. So let's just check our volcanic glass percent again. We might have looked at this before. Back to the lab data, last page. Okay, so in the first 3 centimeters, it's 13%. That's greater than 5. But we need at least like 18 to 25 centimeters or something like that based on the depth requirements. The rest of the section is 4% and 3%. So if we took an average of this, it might be close to 5, I guess. I don't know, but I guess technically we fall short of that requirement. What's the other one here? Aluminum plus half iron times 60 plus volcanic glass percent. So let's go back to our aluminum plus half iron. Let's take a rough average. So it's highest, right? Zoom in a little bit. It's highest right here, 0.44% in the top 3 centimeters, but deeper in the profile, it goes down a little bit. So if we take like a rough kind of weighted average of this, it's going to be about 0.3, I think. So let's just take 0.3 times 60, following the instructions from right here, item B. So aluminum plus half iron will round to about 0.3 times 60. That is 18. Plus the volcanic glass percent, if we say it's about 5%, 18 plus 5 is only 23. It's not 30 or more. So technically, we don't fit the definition of Vitrandic Fragixeralfs. Item of full disclosure here, the official description for this soil profile is a Vitrandic Fragixeralf. So perhaps that was either done in the field where there's where we didn't have the lab data to look at, or maybe a little bit of fudging. This is where it's kind of a gray area here now, because if you rule Vitrandic Fragixeralf out, you don't have a molic, aquic, or inseptic Fragixeralf. It's a typic Fragixeralf. So it probably doesn't make you feel very good to hear that I'm okay with either one, honestly. Typic Fragixeralf works. That's what it like officially by the book keys out as. But you're close. You're really close on this Vitrandic Fragixeralf requirements. It was just short of the 5%. It was pretty close to that 30 or more. So it depends on what your philosophy is with this. It doesn't meet the rules, but you think about who wrote these rules. These are like, they're not, taxonomy rules aren't necessarily set in stone. They're made by us soil scientists to try to do our best to describe the soils that we have. And they change a lot. So I wouldn't take these to be totally non-negotiable rules. And, in my opinion, including something about the volcanic glass is maybe a good idea for this taxonomic name, because if someone were to describe to me this soil as a typic Fragixeralf, it makes me think of the Fragipan, the xeric soil moisture regime, and the alpha sol. And I don't have any clues about any volcanic ash influence in this profile. Whereas I would if you said it was a Vitrandic Fragixeralf, but that's perhaps not fair to the true Vitrandic Fragixeralfs that do meet those official requirements. So either one is fine with me. I'm going to write down both of them. So when I'm taking a look at these after you turn them in, I'll know that I had 2 acceptable responses there. So it could be either Vitrandic or typic Fragixeralf. Okay, so feel free to reach out to me if you don't like that or have more questions about it, but either one is okay. It's up to you to decide what kind of philosophy you want to take as a soil taxonomy professional. All right, either way, there's no extra page number there. That's where it ends. So we've done our subgroup level classification. We're going to skip to chapter 17 now to do our family and series differentia and names. And we'll start with our particle size class. So check our hint again. Our particle size in mineralogy control section is going to be 71 to 157 centimeters. I'm going to tell you when that's important to consider in the hints. This is just the most important section to consider for our particle size class. So looking at our taxonomy book here, this is page 319, 320. Let's see, we can key some of these out. A fine earth, so I'm looking at throughout the control section, if we're substituting a class, less than 10% of the total volume is fine earth component and meets one of these. If there's a lot of like volcanic influence and coarse fragments, it could be pumiceous, cindery, or fragmental. That's not what we have, right? We're less than 5% coarse fragments with the rocks. So now we're on to item B. Fine earth component of 10% or more. Okay, that's us because we're silt loam. If we have andic soil properties, which we don't, so we can't really say it's ashy pumiceous, ashy skeletal, or ashy. Fine earth component with andic soil properties and a water content data medial, we're going to rule these out too. We're going to keep skipping past all these really. Item 4, I think we can rule out as well, right? Gypsum. We don't have gypsum or Y horizons. And 50% or more particles with diameter course. Yeah, I know that's gypsum still. Okay, on to item C. Other mineral soils in the control section, substitute particle size class. A total content of rock fragments plus any artifact. Okay, so section C here is where we've moved past all the volcanic ash. So this is going to be probably where you end up for most of the other pages that you key out, where we're into the more generic soil textures here. They start off very coarse, okay? We have artifacts 2 millimeters or larger, 35% or more. rock fragments, sandy skeletal. Okay, so skeletal means lots of rocks and sandy means pretty coarse. So we know we're a silt loam. We're kind of gonna carefully skip past some of these. So we're not sandy. It's gonna be more silty or fine or something like that. So let's look at number 4 here, a texture class of coarse sand, sand, fine sand, loamy coarse sand, loamy sand, or loamy fine sand. So this is really the bottom left of the triangle where we're really sandy. We know it's not sandy. Okay, texture class of loamy, very fine sand, or finer. That is us, so that includes everything except the really sandy classes. Less than 35% by weight clay, I think that's us. And are in a shallow family, as defined below. That means if you have an R horizon really close to the surface, that's not us. Lithic, arenic, or grossoranic subgroup. I don't think that's us. We're not loamy. Coarse loamy is if you have 15% or more particles, fine sand or coarser, including gravel and artifacts. Let's check what we have in that range. Let's skip back a couple pages. Our texture, okay, zoom in again. From 0.1 to 75 millimeters, right? We're less than 5%. Okay. From 0.1 to 75 millimeters, we needed 15% or more. We don't have that. We're not, wait, 50%, we're not coarse loamy. 15% or more particle. So fine, we're ruling out fine loamy as well. Here's coarse silty, having the fraction less than 75 millimeters in diameter, less than 15% particles with diameters. Yes, that's us because we're 5, less than 15% right there. And in the finer fraction, less than 18% clay. Let's check our clay percent from the section that we're looking at. Our percent clay is starting at 71, 22, 24, 30, and 29. So we're in like the mid 20s, let's say. We're greater than 18. This definition is going to be very similar, except it says 18 to less than 35% by weight clay. Fine silty. There we go. We fit our particle size class. I'm going to put fine silty down right there. Okay. Now for mineralogy. Mineralogy is a little bit interesting, I think. This one's kind of difficult. So what is this? Human transported classes. We're going to skip that. Mineralogy classes right here. Page 325. So let's start looking at these letters here. Letter A, oxasols and candy can have great groups of alpha sols. Nope, that's not us. We are, our great group is Fragixeralf. So we're skipping item A onto item B, other soils. In the mineralogy control section, we have the substitute class that replaces particle size class other than fragmental and have 40% or more gypsum. Skip, we're not hypergypsic. Both a sum of 8 times the silica extracted by ammonium oxalate from the fine earth fraction plus 2 times the iron of 5 or more. Okay, well, let's try this. Amorphic kind of does mean, we're talking about mineralogy here, I guess. So I'm not sure if that's volcanic ash or not, but 8 times. Okay, so we're going to take silica times 8 plus 2 times the iron. So let's go back to our lab data. Look at our extractions here. Zoom in, we have our iron right there and our silica right here. So silica is really low. It's 8 times the silica. Let's take an average of these and say it's 0.03, 0.03 times 4 is 0.24 plus 2 times the iron, right? Let's check the rules here. 8 times the silica plus 2 times the iron. The average iron is going to be 0.35 or so. That times 2 is like 0.7. 0.7 plus 0.24 is 0.94. These are, I'm rounding these numbers. I'm going kind of fast, but that all that is to say it's definitely less than 1. Our sum of 8 times the silica plus 2 times the iron is not 5 or more. So we're going to rule out amorphic. Silica plus 2 times the iron of 5 or more. It's not very hydritic. It's not 30% or more volcanic glass, right? We had 13%, 4%, 3%. It's not 30, so it's not glassy. It's all other soils in section B were mixed. Okay. Now let's say we weren't quite sure about this definition here in B. If we didn't know that this is where we belong, what would we do? Would we say it's mixed and just be done with it? or would we keep going? So let's bookmark this before we write it in. Mixed is one option, but what if we weren't supposed to be in chapter or part B anyway? If we went on to part C, we would see other mineral soils. I think we skip this because of the histosols. Particle size class. Right, none of these minerals really match. Part E, all other soils. Wait, is there a part D that I'm missing? Clay skeletal. All right, parasequic. None of these really fit. These are all talking about clays. Okay, part E, all other soils. With mica grains, we don't have those. It's not micaceous. It's not parasequic, right? Fe2O3. Soil chemists will understand that. Do we have, for item 3, in more than half of the thickness, all the following: no free carbonates. We don't have HCl reactions. A sodium fluoride pH, NaF pH of 8.4 or more. Let's take a look at our sodium fluoride or pH. That is going to be down a little bit, I think. pH and carbonates. Oh, hello. Do we have 5% carbonates? I'm not quite sure about that. Oh no, carbonate percent. Okay, right here is calcium. What is this? Calcium chloride. Okay, that's not calcium carbonate. Never mind. Carbonate is right there. There's nothing there. Don't worry about that one. Okay. NaF sodium fluoride 8.7, 9.0, 8.6. That's greater than 8.4. And a ratio of 1500 kilopascals water to measured clay of 0.6 or more. So let's try this. 1500 kilopascals water. Where is that? Excuse me. 1500 kilopascals water. Where are we looking at for mineralogy still? We're looking at from 70 to the bottom. So we've got about 8, about 10. So we're taking this divided by the clay percentage. Our percent clay down here is on the first page of lab data. Percent clay from 71 is 22, 24, 30, and 29. Let's take an average of that around like 25. Oops, back to the lab data. So our clay is 25, and our 1500 kilopascals water is about 10. So looking at isotopic ratio of kilopascals water, so 10 divided by about 25 is 0.4. It has to be 0.6 or more to be azotic. That's not us. Okay. Siliceous, we don't have 90% by weight or grain count silica. I believe that would be on the last page of lab data. We don't have anything talking about silica. At this point, we're all of the soil properties and it's mixed. So back to our first bookmark, we had mixed to begin with. We got mixed again. That's a pretty good guess, is to go with mixed. If you ever get stuck at a crossroads like that, you can ask around for sure, see which way other people went, or ask me for help. I'm very glad to help steer you in the right direction. Okay, cation exchange activity is the next one. Let's take a look at this. The ratio of cation exchange capacity. Oh no, number 1, cation exchange activity has to have a mixed or siliceous mineralogy class. If you don't have that, you skip activity. Now that doesn't say you leave the box blank, right? You cross it out to prove to me that you evaluated it and you said there's nothing that fits here, so put a dash there to prove to me. And then it also says activity / other. So there, in some cases, there's like a depth requirement. I will put that in the hint, I think, if you need a depth class or something else to go in other. But we do have mixed, so that means we do have a activity class here. Our ratio is cation exchange capacity by 1 normal ammonium acetate extraction to percent clay by weight. So let's take a look at our cation exchange capacity in the lab data. That would be kind of second or third page, maybe. Okay, calculate right here. Ratio divided by clay is our CEC. We're looking at the mineralogy control section. So from this horizon down, 0.39, 0.7, 0.42, 0.42, an average of that is going to be around 0.45 or 0.5, somewhere between 0.4 and 0.6, I think. Let's go back to the keys. If it's 0.6 or more, it's super active. If it's between 0.4 and 0.6, it's active. Okay, that's where we're going to fall out, and we're going to say active. All right, our temperature is easy because we did that right up here. Temperature is frigid. And we have just filled out the table. So our full name is going to be fine silty, mixed, active, frigid, Vitrandic or typic, your preference. I'm not really one to follow the rules of soil taxonomy in cases like these. I would say it's Vitrandic Fragixeralf. I just like including the volcanic glass content in there. I mean, because if you told me it was typic Fragixeralf, that doesn't, like, the volcanic ash influence is nowhere in the name then, and I don't really like that. It's there and it deserves to be represented, I think, even though it doesn't meet the exact letter of the requirements. But typic also works because that is technically what it keys out as. Okay, if the gray group describes the fragipan, this is our follow-up question, what does the subgroup describe in the soil? So in my case, it does describe the volcanic glass content. In your case, if you chose to go typic, it would mean, you know, there's nothing else to really say about it. Like, we've already covered the fragipan. There's no durapan or natric or really BW horizon with nothing else, right? The inseptic would be the subgroup prefix for that. In my case, I would say this describes the volcanic glass content, but your answers may vary. So that is our full demo of the first soil pedon. I wish you guys luck working through the rest of them. I may upload more videos or more walkthroughs because soil taxonomy is pretty complicated. It's pretty frustrating. It just takes a lot of practice to know what you can skip and what you can't, what you have to be really careful about, and how to get off the bus at the right stop. Because if you miss your stop, you'll end up somewhere, but it might not really represent what soil you're talking about. So just as a review, if you want to check your answers, just go through your name, go through the full name, and make sure it represents it, like it seems like a match with the soil you're talking about. So in our case, we covered the xeric moisture regime, we covered the fragipan, and really the texture and the activity and the mineralogy is pretty well covered. So with that, I will end the recording and wish you guys luck. Reach out if you need any more help, and good luck with your soil taxonomy challenge.